Hi everyone, welcome to the slope deflection method for portal frames with inclined legs. So in this session, what we are going to discuss is the analysis of portal frame with inclined legs. For example, if I look at a portal frame with inclined leg, something like this, this is one leg of a portal frame. This is horizontal member, then another member like this. So this frame is subjected to the lateral load. So let us say this is a load P. Now how do we analyze? Let us say this is joint A and joint B and joint C, joint D. Let us discuss only the concept here, then we can take up a problem and we'll try to go for the solving it. So now if you look at carefully, this inclined leg, which is AB, will have a deformation to the right side. If I draw the deformation diagram, it goes like this and something like this. Then this CD will also deform because of this lateral load, but the amount of deformation in the leg AB is always the perpendicular to the member AB, which is very, very important. So this AB, so let us say this B goes to somewhere here as a B dash. So the B and B dash is the delta 1. Very important. So or we call it as a small delta 1. Now if you look at the displacement in CD, the leg, so because of horizontal right hand side load, this also displaces the right hand side, so that here something like this, something like this, right? So goes something like this. So now this C, whichever the point C, will deform to a point this called, let us say, C dash. The C will go to a C dash, right? Now that means the beam will also have a deformation something like this. Right? If I draw a dotted line between connecting between C and C dash, and the connecting between the B and B dash also something like this, the displacement or the deflection in CD is, as I told you, the perpendicular to the member. So this will be the displacement. So that means C dash is your delta 2. This is very important. And since this leg AB is inclined, let us say with an angle of theta 1, this CD with inclination of angle of theta 2 with respect to horizontal. So now, so if you look at the number of unknowns, what we have here is the rotation at B, that means theta B, rotation at C, which is theta C, right? Then the two deflections at B and C. Now remember that amount of lateral deflection at B is not equal to the deflection at the C. Okay, so this delta 1 and delta 2. So these four equations will be coming here, right? So there will be four unknowns. Now to solve this we need four equations, but what we do, we'll try to establish a relation between delta 1 and delta 2, so that we reduce this unknown to a single, so that finally I will have only three unknowns. So the equilibrium equations are two, which are like summation of moment at B equal to 0 and summation of moment at C equal to 0. So these two equilibrium equations, joint equilibrium equations, and one shear equations, the shear equation, which is your horizontal forces at A joint plus at D joint is equal to P. So this is shear equation. So I will be able to solve this problem using these shear equations. So let us look at how this, the relation here, the criticality is finding the relation between delta 1 and delta 2. This is very important. Now, so let us work on that. So let us see how to get this relation. Now, if you try to drop a vertical line here, so if I drop a vertical line from here, okay, now this angle theta 1, that means this will be 90 minus theta 1, right? Now what I'll do, I will take a drop here, vertical like this, vertical drop. This will be, let's say I call it as double dash. So then if I draw carefully here, this will be a B and this is B dash, the defined position, this is the assumed point B double dash. Now you look at here, this angle was 90 minus theta 1, that means this angle, that means this angle here will be again 90 minus theta 1. So this angle is 90 minus theta 1, very important. So what is this BB dash? As I mentioned here, BB dash is delta 1. So this is delta 1. Right? Now it is important to understand what is this B double dash. If this 90 minus theta 1, this will be cos, this will be sin. So if to understand here from this triangle, so the B double dash is nothing but cos of delta 1 times cos of 90 minus theta 1. That means delta 1 sin theta 1. Right? This is your horizontal displacement of joint B. So I'll write down here, this is nothing but my horizontal, right here, horizontal displacement of joint B. Now what is the vertical displacement of joint B? Displacement of joint B, nothing but your B double dash B dash, which is nothing but delta 1 sine of 90 minus theta 1, which is equal to delta 1 cos theta 1. Remember this, very important. Okay, so now let us look at here with the other side at joint C. So what happened at joint C? At joint C, if I drop from the C dash vertically like this and make a horizontal here, right? Now see what happens. If I take again a vertical drop, this is theta 2, so this will be a 90 minus theta 2, right? So 90 minus theta 2, so this is total 90, that means this is theta 2. Clear? This is 90 minus theta 2, so total 90. So 90 minus of 90 minus theta 2 is your theta 2. So this is theta 2. Right? Now this being perpendicular to this, so these two are perpendicular, so this angle must be 90 minus theta 2. That means this angle is theta 2. If I draw separately that C here, if I draw here, this is C, this is C dash, let us say I call it as C double dash, C double dash. So this has become 90 minus theta 2. And what is the displacement? Is this displacement in member CD is this delta 2. Okay. Now what will be the horizontal displacement of joint C? Displacement of joint C is nothing but my C double dash. That is nothing but my delta 2 cos of 90 minus theta 2, which is equal to delta 2 sin theta 2. What will be a vertical displacement of joint C is nothing but my C dash C double dash, which is your delta 2 sin 90 minus theta 2, which is equal to delta 2 cos theta 2. This is very, very important to understand. Okay. So now having understood this, so another important, we know the fundamental assumption here is that the member BC has no axial deformation. Since the member BC has no axial deformation, the horizontal displacement at joint B must be equal to horizontal displacement at joint C. That means B double dash must be equal to C double dash. So B double dash C double dash is equal. So that means your delta 1 sin theta 1 is equal to delta 2 sin theta 2. So here that means I have established a relation. Delta 1 is nothing but delta 2 times sin theta 2 by sin theta 1. So that means I have reduced one unknown here. So this is very important derivation here. This is one important derivation. Second, we know the summation of moment at B joint is equal to 0. This is joint equilibrium equation, which is MBA plus MBC is equal to 0. second joint equilibrium equation, MC is 0, which is your MCB plus MCD is equal to 0, right? Then the shear equation, which is the total horizontal force HA plus HD plus any horizontal force is there, that must be equal to 0. So these three equations are sufficient to solve the problem. Now the one small understanding, clarification I would like to make is, we know what is MBA or MAB. MAB is MFAB plus 2EI by L 2 theta A plus theta B minus 3 delta. This is your delta 1 by L, the length of that member AB. Very important here. Although in this case, if A joint is fixed, this can be 0. Okay, depends upon the boundary condition at A, but this is very important to understand. Now, similarly, MBA is MFBA plus 2EI by L 2 theta B plus theta A minus 3 delta 1 by L. This is also very important. Then let us have the end moments for member BC, horizontal member. So if you look at carefully, MBC, which is MFBC plus 2EI by L of that member 2 theta B plus theta C minus the delta 3 by L times delta. What is the deflection in the member BC? That is very important. What is that member? So if I go back to the structure, we will understand here. Look at here, this member B and C has got deformed and became a shape of B dash C dash. So that means something like this. So this is B dash, this is C dash. So if you see carefully, this is my reference point, right? This is the difference point. This is originally B, originally C double dash or B double dash. So now if with reference to the B dash, the C dash, how much amount has gone up or down is, if I draw this, so this B to C dash is this much is the total amount. The displacement took place in member BC. So this is nothing but this plus this. That means C dash, C double dash plus B dash, B double dash. So that is why I have worked out the total vertical displacement of the joint C and joint B. Here, this one. The sum of this total becomes the total displacement in member BC vertically. That is the delta. Please remember this. So that means this will be your the delta 1 cos theta 1 plus delta 2 cos theta 2. This is very important. Okay, so this completes the equilibrium equation for the member BC. That is end moments for the member BC. Similarly, the MCB is the same thing. MFCB plus 2EI by L 2A by L 2 theta C plus theta B minus 3 by L times delta 1 cos theta 1 plus delta 2 cos theta 2. It's very important. Okay, and anyway I establish relation between delta 1 delta 2, I can substitute here and get only one unknown. Now coming to the next, so that's again here, what is the sign here, the minus or plus. So this, the B joint is displaced downward compared to right hand side, so this will be a negative of that, so minus of minus will be plus here. So this is a plus, very important to have understanding. This will be plus. Now coming to the next is your vertical, which is MCD is MFCD plus 2EI by L 2 theta C plus theta D minus 3 by L, what is that, delta 2. So the displacement of the joint, whichever joint you are taking, must be perpendicular to the member, that means delta 2. This is very important understanding. Of course, depending upon the end conditions, so the theta B can be 0 if the joint D is fixed. Now how to understand about this shear equation. So what is this HA? What is this HD? As we learned previously in the portal frame with the sway case, what we do, we'll try to take up. So let us understand the shear equation. The shear equation, which is HA plus HD plus P is equal to 0. So what is HA? So HA can be obtained by taking this equilibrium part of the member AB. That means if you look at carefully, this is a member AB. So maybe somewhere here I draw. This is A, this is B. Now, so at joint A, there will be a vertical reaction which is VA, or we say RA, and there will be a horizontal reaction called HA. Right? Now, this joint have a movement called MAB, and B also has a movement called MBA. Right? So now this member is inclined at angle of theta 1. So let me write here angle of theta 1. So now what happens? So HA, for this column inclined leg to be equilibrium, I must have the opposite force to be HA. Only then this joint will be, this column will be equilibrium, right? And a vertical force of A. Now this AB is in equilibrium. Only then structure is standing. Very important. Okay. Similarly, let us take the other leg as well, which is something like this. Right. So this is your D point. This is the point C point. So this is also having a reaction RD, vertical RD, horizontal reaction HD, horizontal reaction HD, and this joint will have a movement of MDC, right? Now here also we will have a moment of MCD. We assume all moments are clockwise right now. And so now for the purpose of the equilibrium, if you see carefully, so this particular HD here, there must be a equilibrium of horizontal force, which is LD for equilibrium, right? Now RD should have a downward here, which is RD. Okay, so this column AB and column CD became a equilibrium. Then the B which is there in between should also be equilibrium, which is your B and C must be equilibrium. That means now these forces should be balancing. So RA downward, there must be RA upward, which is nothing but RB is same as RA, which is only then there will be equilibrium, which is nothing but my RB. So here RD downward must be RD upward, is also which is RC. RD is nothing but my RC. Now, right? So now MBA, and so there must be a clockwise movement here on the joint, which is MBC. And here also I must have a movement which is MCB. And now horizontal, you see HA is the horizontal here, HA left hand side, HA must be your right hand side. Here HD is the left hand side arrow, and there must be a right hand side, which is HD. So now I made inclined leg AB, inclined leg CD, and BC a equilibrium. Now simply taking moment at the point B, moment at point B, summation of moment at point C, I will be able to get a HA. So what is that? Summation of moment at point A, which implies MBA plus MAB. Then this particular HA will be your anti-clockwise, so I can write other side HA into this length, right? Length is, let us say, L1. So if I draw a vertical line here, so what is this H into vertical? This one will be a sine theta. So L1 sine theta 1. L1 sine theta 1. So the opposite side is L1 sine theta 1. Then this RA also is there. RA will have a clockwise movement, which is this side. I can say minus RA into this horizontal distance, which is L1 cos theta 1. L1 cos theta 1. If directly the vertical height and horizontal length is given, I can use this here instead of L1 sin theta 1, L1 cos theta 1. If not given, if inclined length is given, then I will convert into sin theta and cos theta 1. Okay, so again in this equation I have H and R. So I have to remove this R also. Similarly, from the CD, I will find out from this what I get. Moment at C, summation of moment at C equals 0. What I am going to get is MCD plus MDC, right, is equal to, I know this angle is your theta 2. If length 1 is L2, right, the vertical distance is your L2 sine theta 2, and horizontal distance your L2 cos theta 2. So now HD into vertical, that means L2 sin theta 2. So HD, which is giving anti-clockwise, I am writing other side. So HD L2 sin theta 2, then RD is going to give anti-clockwise, so I am writing this side, which is RD into horizontal distance, which is L2 cos theta 2, right? Now in both this equation I have RA again unknown and RD again unknown. RA RD again unknown, because to substitute in the shear equation I need HAHD, but again HAHD in terms of RA and RD. So to get this RA RD, I will take the member BC equilibrium, this member, this equilibrium of this member, and taking moment. Okay. Now taking moment of this member BC at, let us say, at point B. So moment at point B is equal to 0. So I am going to get MBC clockwise plus MCB clockwise minus RD into the length of the member BC. Let us say the BC member length is, let us say, L. So into L, right, equal to 0. Okay, so RD or RC are same. So then I can get RD from this equation. Similarly, taking moment at C equal to 0, then I get a RB, which is MBC plus MCB minus, yeah, clockwise. So RB plus RB or RA into L is equal to 0. I can get RA. In this case will be both same if it depends upon your MA, MB, and if at all any UDL load, any point load there in the member BC, accordingly movement will be taken. So this way, so this RA RD substituted into these equations, get HA HD, and back substituting into this equation. So finally I will have the quotient terms and theta B, theta C, and let us say delta 1 or delta 2, you can substitute into the one of that, is your constant terms. So once solve delta 2, I can find delta 1 because I have a relation between delta 1 delta 2. Thank you.